For the two-axis bending case, we now have our kinematics and our equilibrium relationships. Let's go ahead and complement those with the constitutive relation, and we'll assume the elastic case. So we have a normal stress in the x direction is equal to the Young's modulus E times the normal strain in the x direction. So epsilon xx and sigma xx are the bending strain and the bending stress respectively. And let's go ahead and see what this implies for the bending of two-axis beams. So let's suppose that at a given cross-section I know what mz, my, and r are, so those are given. And let's go ahead and determine what the bending stresses as a function of y and z look like on the cross-section. So I'll go ahead and consider the case of a rectangular cross-section, b by h in dimensions, and I'll put my coordinate frame centered right at the center of this cross-section. So, and actually it doesn't matter how I set this up because of the way I've written out my kinematics. I could put the coordinate frame origin at one of the corners of the rectangle if I wanted, but it's usually best to put it at the center right here. Now, the thing that I know is that the bending strains are going to be epsilon naught minus the curvature about the z-axis times y plus the curvature about the y-axis times z. And that's going to tell me what the stresses are. The stresses are going to be linear on the cross-section, but they're linear in a much more complicated fashion than I had before here because of the y and z dependency. But I have expressions for those. Now, I don't know in this expression yet what kappa z and kappa y are, but I can use the equations for the resultants and their connections to the stresses to determine those. So if I take the expression for the force resultant in the x direction, I have r is equal to the integral of over the cross-sectional area of sigma xx here. And if I plug in my expression for sigma xx into that integral, I can actually compute this integral, and I find out that I get Ea epsilon naught. And notice that the kappa's disappeared, and that's because I placed my coordinate origin right at the center of the cross-section. So when I integrate y over the cross-section, I'm going to get 0. So that kind of simplifies things. And that allows me to determine, say, for instance, what epsilon naught is in my expression for the stress. I find out that epsilon naught is equal to r divided by AE. Okay, and now let me try and go ahead and figure out what these other two constants are, the kappa z and the kappa y are, and I'll use the resultant relationship for mz and my to determine those. So if I write out the expression for mz, it's minus y times sigma xx integrated over the cross-section. And if I compute this integral, I'm going to get I z, the moment of inertia about the z-axis, times e times kappa z. The integral for the z here multiplied by the y will give me 0 because of how I've set up my coordinate origin. And likewise, the integral for the epsilon naught term will also come out to 0. So I only end up with one of my unknowns, the kappa z, in my relationship. And so now I know what the curvature about the z-axis is the moment about the z-axis divided by eiz in this case. We can kind of step forward here and go ahead and look at the moment about the y-axis. The expression for the moment about the y-axis is z times the stress. And I can compute this integral, and if I do that, I get eiy, so moment of inertia about the y-axis, times kappa y. And the other two integrals, the integral involving epsilon naught and the integral involving kappa z, come out to 0, again because of how I've placed my coordinate origin. So placement of the coordinate origin is very important here to make the system of equations as simple as possible. This allows me to solve for kappa y, and I get my, moment about the y-axis, divided by eiy, and that allows me to determine what kappa y is. So I can plug these three results into my expression for sigma z that I started with, and I have that sigma z is equal to r over a minus mzy over iz plus myz over iy. And so I end up with a linear function of both y and z in this situation. So if I ignore the first term, which is due to axial forces, and the second term, which is due to bending moments about the y-axis, you'll see that I have the expression that I had before, minus my over I, and now I am being very particular here about moment about the z-axis and moment of inertia about the z-axis. And then I pick up additional terms, so I add in any axial stress, or stress due to axial forces, and I add in stresses due to moments about the y-axis. And so I end up with this sort of situation of superposition here. Note also that the placement of the coordinate system was really useful. So in particular, I placed my coordinate origin so that the first moment of the area about the z-axis, so qz, was equal to 0, and the first moment of the area about the y-axis, namely qy, that was also equal to 0. And that the cross moment of inertia iyz, which is the integral of y times z over the cross-section, would also be equal to 0. If you don't place your cross-sections or your coordinate frame in the situation where these three integrals are equal to 0, then, well, those terms appear in your relationships, and then you'll have to solve a system of equations to determine epsilon naught, kappa z, and kappa y. Okay, but the other thing that's important to note here is this superposition type of result that we have for the stresses, that we can compute stresses for forces, axial forces, then we can compute stresses due to bending about the z-axis and add those in, and we can compute stresses due to bending about the y-axis and add those in, and that gives us a superposition of the behavior here. And superposition holds whenever you have linear problems. So when we have linear elasticity, we will always have this ability to compute stresses via superposition.